Okay, I think we can start now. So hello everyone. Today we're very happy to have Hannah Lu from Stanford University presenting to us. Hannah is a soon-to-graduate PhD student in energy resources engineering at Stanford University. She received her BS from Shanghai Jiaotong University in 2015, MS from University of Wisconsin-Madison in 2018. Both major in mathematics, and she joined Professor Daniel Tartakovsky's group at Stanford since 2018, and she will soon defend her thesis and move to MIT as a postdoc. Hannah's research involves several aspects of scientific computing and modeling, especially the reduced order modeling, which she will talk about today. And she is interested in applying these computing and modeling methods into environmental fluid mechanics and biomedical studies. So welcome, Hannah, and please take it away.
Thank you, Jianhua, for the introduction. I'm very happy to present my work with my advisor, Daniel Tartakovsky, on dynamic mode decomposition, mostly for reduced order modeling in transport problems. So my research interests lie at the intersection of scientific computing and data-driven modeling. Data-driven modeling, or say classical machine learning, arises from computer science in applications, for example, image classification, where large amounts of data are available, but no physics or equations there. The concept of prediction and error is more qualitative than quantitative. On the other end, physics-based models have been studied for centuries. There are little amounts of data available and they're usually difficult or expensive to obtain. But the concepts of error and accuracy are universal, and the concept of prediction is mostly quantitative. Nowadays, with the development of data science, modeling for the most challenging multi-scale, multi-physics, complex systems has been driven to this intermediate area where the models are constructed by some data and some physics. So this intersection of scientific computing and machine learning is referred to as scientific machine learning. One important part of this area is to look for cheap but accurate surrogates of reduced dimension. Generally, we are going to face high dimensional ODEs eventually after discretization. So although today we have more and more advanced computational capacity, it is still very expensive to solve the full high dimensional system, especially in optimization, control, and uncertainty quantification problems, where thousands of simulations need to be run. So many research has been done in looking for meaningful representatives of reduced dimension. A good ROM can obtain the most informative subspace as efficient as possible and preserve the characteristics of the system as much as possible. Like you want to simplify the instant, but you still want it to be recognized as instant. The popular model reduction technique I studied is dynamic mode decomposition. For a general PDE, where this D involves spatial differential operators, suppose we are given the data matrix from M snapshots of the fully resolved solution, which of very high dimension, capital N, due to spatial discretization. Then DMD looks for a reduced order model, U tilde, of much smaller dimension R. It is driven by this reduced order best fit linear operator K tilde. As you can see, DMD is a data-driven approach, and the resulting ROM is a linear model. The nonlinearity in the differential operator D of the high fidelity model is transformed into a linear operator K tilde in the resulting ROM through the so-called Koopman operator theory. The design of the Koopman operator is closely related to the knowledge about the underlying physics, which I will explain in the next few slides. So the speed up of this ROM is obtained by the reduced dimension and the iteration-free feature. Many fantastic works from people like Schmidt, Brunton, Coos, and so on. DMD is going to use the correlation of the column data matrix. We separate the data matrix in two parts. X1 is snapshots from time 1 to n-1, and X2 is from time 2 to n. We want to find the best fit linear operator K, relating X2 equals K working on X1. So we first do a truncated SVD of X1 and using pseudo inverse to approximate the linear operator K. But remember, this K is still n by n very large matrix. So we want to use the POD projection to obtain the R by R much smaller matrix K tilde to approximate K. Then we compute the eigen-decomposition of K tilde and reconstruct the eigen-decomposition of K by the projection. Once we have the eigenvalue and eigen vectors of the linear operator K, we can write out the solution in any future time by using this analytical form. So here is an example of DMD application in a flow problem. We have a periodic solution because of the periodic boundary condition at the left wall x equals 0. We use the data of the solution for one period, and then we can construct a very accurate surrogate for DMD for the rest of the simulation time. We can barely see any eyeball difference between the fully resolved solution and the model, the reduced model constructed by DMD. So my PhD thesis introduces a physics-aware dynamic mode decomposition framework. It combines the popular data-driven tool DMD, which uses a best linear approximation to create a fast, reduced-order model for complex systems. We combine it with physics-aware ingredients. It then successfully resolves several challenges in traditional DMD-based ROMs, including the translational problems for advection-dominated systems, shock capturing, and handling the inhomogeneity. So we have seen the previous video that DMD has been applied to many successful cases of data-driven regression. But then we have these coming questions. How accurate is DMD in terms of prediction? So here, prediction, we mean in the extrapolation regime, not in the interpolation regime of the given data. And what does this error depend on, and how to improve it? So this is my first project, and we derived a predictive error bound for DMD in linear and nonlinear flow problems, answering all of these questions above. The main results we have here is to define the error between the fully resolved solution at later time and the DMD prediction at later time by En. Then this error is bounded by this term. So here, phi again is the matrix whose columns are the DMD modes, and epsilon m is a constant only depending on the number of snapshots n. It has been proved by other groups that in the weak sense, this constant epsilon m goes to 0 as number of snapshots goes to infinity. This is consistent with our intuition. When unlimited number of data available, you basically know everything about the system. And for a given number of snapshots, there are many variational forms of DMD to improve the local truncation error epsilon m. And the term En is fixed and designed to be minimized in DMD algorithm. So if the local truncation error epsilon m is of order p accuracy, then the global truncation error is of p-1 accuracy. So let's see a linear diffusion equation with periodic boundary. It is a simplified 1D version of the previous video. the space is discretized into 500 intervals, and the time domain is discretized into 500 intervals. We use the first 200 snapshots and construct a very accurate ROM compared to the resolved solution. As you can see, 200 snapshots among the 500 discretization has already covered one period of the solution, and so DMD learns the feature of the dynamics. Our error bound in the bottom figure also indicates that the prediction is under reasonable error control. However, if only 100 snapshots are taken, as we can see from the previous figure, it hasn't covered one period of the solution, then the error will blow up, and our error bound also successfully indicate the failure. So next, let's see the connection of DMD with Koopman operator theory, which will allow us to tackle more nonlinear problems. Koopman operator is an infinite dimensional linear operator that acts on observable function G, and it outputs the observation of the right-hand side dynamic F. So in this parallel graph, we can see clearly the nonlinear flow map capital F gives evolution of U in the state space, and the linear Koopman operator K gives evolution of Y in the observable space. And these two are linked by the observable function G. So the advantage here is now we transform the finite dimensional nonlinear problem into an infinite dimensional but linear problem. Then we can make use of the analytical solution of the linear system and DMD algorithm to do the rank truncation. As you can see now, the key is how to find this observable function G. So next, I will show you how we design this observable function G in several challenging scenarios. So first, we will see a challenge in reduce out model for advection-dominated problem. Here is the solution of an advection-dominated advection diffusion equation. X-axis here is space, y-axis here is the solution U, and the solid lines are reference solution at different times. The dashed lines are reduced out model solution obtained by standard DMD. The snapshots data are collected from the black line to the blue line, but the standard DMD ROM cannot get an accurate prediction for the future green line and red line. If we increase the rank truncation from 20 to 30, it still doesn't help. So these results highlight the main challenge translational problem posed for the singular value decomposition-based methods. Given the first 250 snapshots data from the black line to the blue line, SVD extracts the dominant DMD modes phi I shown here from the data. So given the first 250 snapshots data, these DMD modes phi I only has fluctuations from the region where the wave encountered. In our example, the subdomain from 0 to 1. But as time increases, the wave solution encounters the other part of the computational domain. In our example, at later times, the dominant signal is in the right part of the domain from 1 to 2. But we can observe that the dominant DMD modes only have fluctuations in the subdomain 0 to 1 and stay flat 0 in the subdomain 1 to 2. So that explains the poor performance of DMD. To solve this problem, we proposed a Lagrangian DMD framework. We first reformulate the general flow and transport problem in a Lagrangian framework and record both the solution and the characteristic lines in the data matrix. Then we concatenate the characteristic line and the solution as the observable and insert it into the DMD algorithm. It makes physical sense because in advection-dominated problem, the characteristic lines are one of the most important physical quantity that needs to be extracted as an important feature. So we tested this framework on linear advection diffusion equation, and nonlinear cases for viscous Burgers equation. It all worked very well. So here again, snapshot data are collected from black line to blue line, and accurate predictions can be made for later time. We also compared the computational time in each cases using Lagrangian DMD and the standard full-scale solutions. As we can see, the speed up is impressive, especially for complicated dynamics, the nonlinear viscous Burgers equation. In all of the previous cases, you may notice we only considered shock-free scenarios, because as we know, once a shock is formed, one has to be very careful using the Lagrangian framework. For this Burgers equation with shocks, if we do the discretization as before, it will give us unphysical overshoot solution, even in the fully resolved Lagrangian framework. And the DMD, it will just follow the wrong Lagrangian solution blindly. So if we apply the discretization carefully, so here we used the backward semi-Lagrangian method, then the full Lagrangian scheme will give us the right physical solution with shock features. However, the DMD Lagrangian suffers from instability once a shock is formed. The moving Lagrangian grids are distorted once the characteristic lines meet each other in the interface where the sharp gradients of U occurs. When the characteristic lines meet each other, we know that one arrival location of X is corresponding to two different departure values of U. However, the DMD mode's projection from the high fidelity model to the low fidelity model cannot keep this topological information of this multiple value mapping in the round process. So this great distortion happens. Let's take a close look at a shock. Shocks cause a lot of troubles, especially numerically, because it is bad in terms of a function. If we go back to calculus 101, we know that the definition of a function is the output of a function can only be traced back to a unique input. But in the shock interface, we actually nearly have one X gives two different values of U. However, if we swap the input and output or rotate the graph, we can see now the interface of the shock becomes a nice function. In another word, U of X is about bad function, but X of U is a nice function in the shock interface. So this is defined as hodograph transform by Hamilton. Let's see a reformulation example of Burgers equation. Consider a Burgers equation with only one shock that is developed from smooth initial data in finite time, which means we need these following assumptions for the initial value of U to be satisfied. And visually, it assumes an initial data of this type. Then in terms of X of U, which is the inverse of U of X, and also the hodograph transform of U of X, the following assumptions about X0 need to be satisfied. And here is the example of X0 as a function of U. Then before shock time, this simple equation needs to be satisfied, and the shock formation time can be calculated analytically depending on the initial data. Then after shock forms, we can calculate the shock speed by the famous Rankine-Hugonot condition. Here, the value of the left and the right U1 and U2 are determined by this system of ODEs. And then the shock location XC is also determined by this function. And it is starting from the initial time T star, which can be calculated as before. So in summary, before shock, we have this simple equation, and after shock, we have two parts. The shock is propagating in the speed calculated by Rankine-Hugoniot condition, and the rest part will still honor the before shock equation. So for general initial condition, we need to decompose the initial data into monotonic increasing part and the monotonic decreasing part. The monotonic increasing part, which gives us rarefaction, will simply follow this before shock equation. And this hodograph reformulation can be applied to general hyperbolic conservation laws with convex fluxes, for example, Berkeley-Leverett equation. So in the algorithm, we will take snapshot solution after hodograph transform. All of these X are discretized in U space and become the first part of the observables. The last observable involves shock information, and they are concatenated together in this observable data matrix Y. And of course, the data matrix should include the data after the shock is formed. And some practical details need to be done to pre-process the data matrix a little bit. For example, we mentioned that initial data needs to be decomposed into monotonic increasing part and decreasing parts. I will explain a little bit more in the numerical examples in the next slides. Finally, we input the observable data matrix into DMD algorithm and get a reduced order model for the observable Y. Then we can use the inverse transform to get back to the state space. So the first example is the previous failure case, the Burger's equation with a Gaussian type initial data. It will cause rarefaction and shock at the same time. So first, we need to decompose the initial data into two parts. The left part gives us rarefaction, and we use the before shock equation. The right part gives us shock, and the shock speed is changing because the left value of the shock is changing with time. So we have to collect the data after shock forms, and also record the intersection of these two parts in the data matrix as the last observable, because it gives the left value of the shock that determines the shock speed. So the data is collected from the black line to the blue line, and we can see the DMD reduced order model is accurate not only in the interpolation regime, but also accurate in the prediction regime at later time. So next, we see a one-dimensional solid shock tube problem. The solution is a mixture of rarefaction wave and a shock. This top figure shows the failure of the standard Eulerian DMD to construct a ROM in the X rows plane. Similar unsatisfactory performances for the pressure and the velocity U. So the data is again collected from the black line to the blue line, but prediction at the future time green line is pretty bad. However, our hodograph-based physics-aware DMD resolved this challenge. X as a function of rho is selected as the observable, and our ROM can make a very accurate predictions at future time, showing this green line and red line. So the last project we studied is an improvement of DMD for inhomogeneous problems. Let's take a look at an inhomogeneous PDE. So the inhomogeneity can come from the source term Sx or from the boundary conditions. After spatial discretization, it becomes a coupled nonlinear ODE, where this little s comes from the inhomogeneity in the source term and the boundary conditions. Analytically, there exists a flow map phi that determines the solution at a later time. So let's revisit standard DMD. We sorted the snapshots data in an input-output pair X and Y. X is the current time solution and Y is the next time step solution. And they are forwarded by this flow map phi of delta t. And then DMD aims at finding the best fit linear operator A so that Y can be best approximated by AX for all of the M snapshots data. In another word, A is determined by this least square minimization problem. So in practice, without considering the rank reduction, A can be determined by computing Y times X pseudo inverse. Then in order to cope with this potential inhomogeneity of the underlying dynamics, the following modification with a bias B is made. So it is made in another paper. Sorry, I forgot to add a reference here. The name-it generalized DMD. So similarly, this AG and B can be obtained by solving a least square problem. And in practice, we can extend the data matrix X into this X tutor and compute AG and B by Y times this pseudo inverse of X tutor. Next, we can rewrite the previous matrix A into identity matrix plus B so that B actually provides an approximation of the so-called effective increment per psi delta t instead of the flow map phi delta t. So this idea comes from the well-known residual network from the computer science community. So although mathematically they're equivalent, but this simple transformation proved to improve neural network performances and become very popular in the machine learning community. So we borrow this idea in DMD and we call it residual DMD. And finally, we combine the idea of generalized DMD and residual DMD, and we call it extended DMD. So we can simply prove that in the least square sense, this generalized DMD can fit the M snapshots data X and Y better than standard DMD. So this equality is only achieved when the bias equals 0. It is very intuitive as the bias term adds more degrees of freedom to the model. So similarly, we can prove that the XDMD can fit the data better than residual DMD in the least square sense. Then under the Lipschitz continuous assumption about the dynamic, we can prove that in this weak sense inequality, meaning the generalized DMD model is always a tighter approximation to the true flow map. And then we can derive the error bound for standard DMD and generalized DMD respectively. Since in the weak sense, this phi delta t minus AG minus B is less than this phi delta t minus A, we can say that generalized DMD always has a tighter error bound than the standard DMD. And similarly, the extended DMD has a tighter error bound than the residual DMD. So we test the generalizability of DMD and extended DMD to new inputs. Generalizability means a model's ability to adapt to new, previously unseen data in the training data. So with the validated generalizability, we can use DMD or extended DMD model as surrogate to accelerate, for example, expensive Markov chain Monte Carlo sampling in inverse problems. So a typical setting of this type of problems is solute transport in groundwater flow. So here, H is the hydraulic head, K is the hydraulic conductivity of a heterogeneous subsurface environment. The domain is 128 times 64 rectangular, and U is the contaminant concentration with the Dirichlet boundary condition at left and the Newman boundary condition at the other three sides. So for training, we generate 2,000 samples of the initial condition, satisfying this distribution. For each initial sample, we solve the contaminant concentration until T equals 80. And here is an example of one realization. Then we collect the 2,000 pairs where the input is the initial condition and the output is the contaminant concentration at T equals 80. Then our goal is to test the ability of the models to predict the contaminant concentration for other initial conditions. For example, this line source. This top figure is the reference dynamics generated from this line source. The quantity of interest is the solute concentration map at T equals 80. So this bottom figure compares the ability of DMD and extended DMD to predict the quantity of interest for an initial condition that is totally different from the training data. As we can see, the extended DMD performs well in this generalizability test, but the DMD presents a totally wrong concentration map because of its failure to handle the inhomogeneity. And the prediction error is largest in the left boundary, where the inhomogeneous Dirichlet boundary condition is prescribed. So to conclude, we tackled several problems and challenges in reduced order models using DMD and published in 4 papers listed below. This physics-aware DMD framework has been rapidly adopted by engineers in faster predictions for geopotential fields, wind farms, and real-time control for robotic systems, accelerated identification for contaminant transport, and so on. So going forward, there are some ongoing projects. One is what I have been working on with Professor Benjamin P. Hestorfer from NYU Prompt on how to construct reduced order models for general advection-dominated systems with multiple variables in multiple dimensions. It is not a straightforward extension from the 1D problem. Remember, in 1D, the difficulty in the dominant advection is resolved by the awareness of the characteristics in the Lagrangian reformulation. However, the counterpart in multiple variable, multiple dimensional system is not clear, so making this problem fundamentally different. So the idea here is to use the so-called random transform. Here I'm showing preliminary results for 2D acoustic equations with 3 variables, pressure and velocity u and v. Here is a full solution of pressure, for example. On random space, the acoustic equation becomes a family of 1D advection subproblems. For each 1D subproblems, we can construct reduced order models using Lagrangian DMD as before. Then the inverse random transform allows us to going back to the state space, and we can get an accurate reduced order model showing here. So again, what helps us here is the physical ingredient random transform. Another ongoing project is about doing parametric reduced order models for complex parametric systems. For example, this is a 2-dimensional flow of an incompressible fluid around an impermeable circle. The flow is driven by an external imposed pressure gradient and described described by the nonlinear Navier-Stokes equation. The quantity of interest here is the magnitude of the flow velocity, which is a 20,000 dimensional vector. So we are interested in the magnitude of the flow velocity patterns for different dynamic viscosities, which is the parameter input here. So given the training data, the first row is operating at viscosity 1/400. The second row is operating at viscosity 1/800. So of course, we can build a ROM for each of these two parameter points. But can we derive the ROM for another parameter point where the viscosity is 1/600 without running the expensive high fidelity model of this 20,000 dimension? So we have this ongoing work where we can use DMD as a surrogate linear model and interpolate the training reduced order basis on quotient manifolds and interpolate the training parametric ROM on the metric manifolds to directly give us an accurate parametric ROM with much reduced dimension of 10 for the new parameter point here, viscosity 1/600. And here the ROM is used for with respect to the parameter space interpolation instead of the time horizon extrapolation. So here's the end of my presentation. Thank you for your attention, and I'm ready to answer any questions you have.
Yeah, thanks, Hannah, for the wonderful talk. I think if you have questions, please raise your hand or type your question into the chat box. I think maybe people need some time to digest a little bit. Okay, Tianze has a question.
Thank you, Hannah, for the great talk. Since I'm not in this field, I'm a little bit confused over how your method can be applied to solve real-world problems. So based on my understanding, the goal is to solve some partial differential equations, but you have data input from some experiments or observations of some type to aid in this process. Is that correct?
Yes, but I will take a step back a little bit. So for now, we are not really using experimental data because, as you know, it's experimental data has a lot of problem with like noise and it has some modeling error. So right now, the data we are using is simulation data generated from the high fidelity model. So in another word, it is noisy free.
Okay, but since the goal is to solve the PDE, how did you generate those data without solving the PDE?
Sorry, I didn't hear you. My connection seems.
Oh yeah, right.
Yeah.
There seems to be some.
Can you repeat it?
Yeah.
Yes.
So you said you are solving. So the goal is to solve the PDE, but how did you get the results without solving the PDE? In other words, how did you get the simulation data? Did you use like simpler models, or?
Yeah, that's a good question. So first of all, you have to have some of the fully resolved solutions, the expensive simulation. So what I'm showing here, first of all, you have to have some of that. And then you're going to use this expensive data. And so the framework allows you to get some cheap predictions for some future time. Then during the future time, you can use a cheap model instead of simulate the expensive model.
And
also, can I add to that?
Yes.
So in real applications that we are looking at, sometimes these outputs are so huge that you cannot understand what your model is generating. So that this allows you to extract information from your terabytes of simulations. And these simulations very often, the outputs are so big that you cannot afford to store every time step because you would run out of memory and you know, hard drive space. So this allows you to obtain low dimensional representation of your output of your high fidelity model. Also,
I see. So it can basically help you understand your results better.
Or also store it, because you hopefully could reduce the dimensionality of
Right. Okay, great. Thank you.
Dan, please.
Yeah, great talk, Hannah. This was a lot to process. I'm still thinking about it and processing it. That's an amazing amount of work you've done. I was wondering, it seems like you need training data in order to sort of design the low rank approximation to the high fidelity model. Do you know what sort of conditions you need on the training data? Like how far into the future, for example, if it's a time-dependent problem, can you extrapolate based on training data from, say, T1 to Tn? You know, how far into the future can you extrapolate? And can you, are there sort of bounds on what you can and can't know in future times based on training data that's limited in time or in space?
Yeah, that's a great question. So one thing we want to do this extrapolation accuracy is we want to know like how many data we want to use in the training and how far we can do the prediction, how accurate it can be. And our results, as you can see, like for this example, so the accuracy and the number of training data you need depends on the dynamic itself. So for this example, like the data, if it see the pattern of one period, then it can do the prediction for the next pattern. But however, if you're not collect enough data to see the pattern, then the information in the data is not enough to do accurate prediction. So in a lot of sense, back to the question in short, is the number of snapshots and the frequency to collect the data depends on a lot of things, and mostly I think it depends on the underlying dynamics. If Daniel has anything to add.
Yeah, no, that's right. But I think intuitively, like with any machine learning, the system has to, the data have to represent possible conditions. Like so they don't extrapolate into regimes that are unseen. You know, just like Google traffic. If a bridge falls, clearly Google would not be helpful, right? Google Maps would not be helpful.
Right. So it has to have seen the dynamics
Right.
in the past in order to be able to predict it into the future.
Right.
That makes sense. So this is sort of a good case or a good application for this method would be a system where you're pretty sure that you understand those dynamics well, but you want a cheap way of doing, of predicting future behavior and of both in terms of memory and in terms of computational cost.
Yeah, that's right.
Awesome. Great talk, by the way.
Thank you.
Maybe I can ask a question. So I think your thesis developed methods for the transport type of PDEs. What's your perspective on similar questions, similar methods that are applied to other types of PDEs like wave equation, other things? What's your thoughts on that?
Yeah, I think wave equation also works. So this, as long as, so the main thing here is this Lagrangian reformulation only works for 1D, not 1D, only works for one variable. It also works for 2D. We have a 2D cases in our paper. So one thing is it cannot. So for a shock scenario, you need this hodograph transform. But for smooth solution, this Lagrangian DMD works. But for higher variable in higher dimension, as I mentioned in an ongoing work, the characteristic lines becomes different for multiple variables in multiple dimensions. So then you cannot construct this Lagrangian DMD framework. So here we use the random transform. And again, for advection-dominated problem with shock scenarios, you have to use this hodograph transform here. And this hodograph transform also has some limitations. Nowadays, the theory is not so clear to generalize to multiple dimensional, multivariable problems. It has a clear form for general scalar conservation laws. So there are some limitations, I believe, for certain kinds of problems. But we take one step here, yeah.
And
Daniel,
Hannah,
please add.
you do have results for the wave equation, right?
I think we have one in the paper. Yeah, I'm not showing one here, but yeah, I think we have one. Yeah.
Other questions from the audience? Okay, so if we don't have more questions, like thank Hannah again for the wonderful talk, and we wish you a good luck with your or your graduation. Yeah.
Thank you.
Yeah, thanks for joining us.
Thank you for having me here. Bye.
Thanks, Hannah.
Bye.
Stop recording.